So we're going to go in a kind of an awkward feeling direction, at least awkward feeling at first, because what we're going to talk about is where something will have a tendency to rotate. And then we're going to go into forces that make things rotate, torque. So the where things tend to rotate come in, if you think about so center of mass, I should say specifically. If you think about trucks or Jeeps with, that are raised, and you'll hear people talking about them being really tippy. So if you go around a sharp corner where you can have a problem with the car rolling over. That comes from the placement of the center of mass because it's raised so far up off of the roadway where the center of mass of that vehicle lives as it's turning, where it's going to naturally want to rotate. That's its center of mass. That's its problem. If you see, or if you've ever gone diving, off the diving board, or done any kind of gymnastics, the way your body, the pivot point, I guess you could call it, of your body's natural rotation is about your center of mass, which tends to be right around our trunk or our derrieres. So how we mathematically define that, and we're going to do the algebra version first, and then I'll talk a little bit about the calculus and how we can use it for kind of odd-shaped things, is we look at adding up. So if I have a rod like this, what I'm going to do is like add up all of the little pieces of this rod. And then the distance away from the center of mass, I can pick any point I want to measure from. So if I wanted to go like from here, take this as my x equals 0, then everything would be measured incrementally coming away from that x equals 0 spot. And I'd be adding up all those teeny tiny masses. So it's a little bit more difficult to think about in terms of like an evenly distributed mass, which is most of what we're going to do. So we're going to start off with, instead of doing a bar, with these like arrangements of masses placed on, and then let's go ahead and make a line here. Oops, there we go. Like I'm going to have all of these masses placed along this line. And I want to know if I make like this the end of the pole, and we'll call it like a massless pole, just to make life easier. I want to know what the center of mass of this thing is. So if I throw it up into the air and give it a little bit of a spin, where is it going to tend to rotate at? And it's going to rotate where most of the mass is congregated. It's going to be its pivot point. So let's see. What would I do? I'd say this mass here is about 1 meter away from this axis. So I have 2 kilograms times this 1 meter. And then I just move on to the next one, plus another 2 kilograms. Let's see, this thing to this thing is 6 meters, so this is representing 5 meters away. So at 5 meters. And then plus 2 kilograms divided or times the 6 meters away. Let's see, and then we just kind of divide it by, and that's going to be the total amount of mass. So you can think of this as the sum of the masses on the bottom, and on the top, the sum of the masses times their position. So the way we like to note this would be like mi xi, from I equals 1 to wherever, however far we're going out. So mi xi, that would be like m1 x1, and then moving up the next letter of the alphabet, if you will, would be m2 x2 or mj xj. That's all that means. So it's the sum of the mass times the position plus, or I'm sorry, divided by the sum of the total masses. So the sum of my total masses, well, I have 6 kilograms on the bottom here. So what do I get? I get, let's see, 2 plus 10. What did I just write? That is not a 10. 2 plus 10 plus 12. 12 plus 12, otherwise known as 24. And what are my units? I have kilograms times meters divided by 6 kilograms kilograms cancel, and that indeed gives me units of meters. So 4 meters. So what is that saying? If I throw it up in the air, I am going to rotate right around here. I mean, it's not a clearly defined distance, but right about there. And that should make sense because that is closer to where my 2 kilograms are. It's not going to be right on the 5 meter 2 kilogram because I still have this mass over here that has to be accounted for. So that's that center of mass at that point. Let's ramp it up because you have to know that we aren't going to do things that are always in terms of just x. We're going to have a lot of two-dimensional things. So what are we going to do here? I have a center of mass for my x position and a center of mass for my y position. So what I want you to do is pause this, and before you do anything, let's go ahead and make a note that we know that this is 18, that all sides are 18 meters. Why am I writing it so close to the writing? 18 meters. The trick here is I can define my axes anywhere. So long as I stay consistent, I will find the point on that axis relative to all of these masses, which are cars in this case, and I will get the same answer no matter what axes I define. So you choose one. What's going to make your life the easiest? And let's go with that. Okay. So I could go like this. I'm going to call that my y, and this my x. And I'm going to go even more wild and crazy, and I'm going to define up and to the left as positive. What? Yeah, so I don't have to do negative numbers, just because I have an aversion to those. So if I can avoid it, I do. So let's see. What do I have I done for myself? Let's start with our x. So here is my x-axis. This will be 0, x equals 0. And this will be x equals 18. So what have I done for myself? I have a thing in the sum on my x-axis. So the sum is going to be, well, this is going to be my 1,200 kilograms times 0, because this is the point that I'm looking at from the x-axis. And the same with this one. That's 1,200 kilograms times 0. It's sitting right on the x-axis. So all I have is this one, my 18 meters. I was going to call that kilograms, that's wrong, times 1,200 kilograms divided by 3 times 1,200 kilograms. So what does this give me? This is meters. Oops, what am I? Yeah, that's not meters. We're getting a unit that doesn't live there. That's the total mass. So the 3 times 1,200 is just, remember, M1, M2, and M3 are equal. So it's just 3 of those fellas. No units with the 3. So my kilograms and kilograms cancel. And it asks you my 1,200s. Oops. So that gives me an x equals 6 meters. So about a third of the way over. Not about a third. It is a third. So I'm horrible at visually estimating distances. We'll call that a third. Call this 6 meters. That's my x. Now let's do my y. Okay, and I just lied to myself. There is no y on this page. So let's just write it out. My y center of mass then. Let's see. This is my y-axis. And this is my y equals 0. So that means I only have the 1 on the y. Because from y equals 0, these two are 0. So again, I'm going to have just the one up here. Oh, I feel like I don't need to do any math because I have this symmetry about this. Again, I have 18 meters away for that one mass from y equals 0. And the same 12, so my y center of mass is also going to be at 6 meters. So about a third. So my pivot point, the center of mass for which this thing is going to naturally rotate, is sitting about right there at 6 and 6. And then we can kind of look at that and then, okay, if I'm about a third of the way, I'm just kind of splitting the difference. I'm getting closer to where all of the masses are clustered. So that is a good approximation. So now what I want you to do is prove for yourself that what I just did is correct and it isn't voodoo. How do you do that? Choose a different axis. So make this one, like make this x equals 0. And then y equals 0. So then you'd have, let's see, 2 on the x, and then on the y, still just the 1. And see where you come up with. You're going to get the same thing.